All right, everyone. Is everyone settled in? Let's get started. Hope you've all had a good weekend. Mine was a little rough, so I will be asking questions of the audience to help me out today. We're going to be talking about homology detection and benchmarking. Now, who here does not recognize this figure? Okay, so you've not read the paper for today. Everyone else has seen this before? Excellent, moving on then. Now, this is not a very difficult topic, but there is a bit of math involved. So if I go too fast at any point, please just raise your fingers and we'll slow down and go over it again. Okay? Now, what I hope that you'll take home from this is that benchmarking is both a very common and a very important task in bioinformatics as a whole, and specifically when trying to develop tools in this field. What we're going to be talking about is looking for a needle in the haystack. You've been working on your projects, and in these projects you have to find homologous relationships between proteins. Now, the amount of relationships between proteins is the number of proteins squared divided by 2, but the amount of homologous relationships between them is far, far less. So that's the needle versus our haystack. The way in which you score your benchmarking really depends on what you compare it with, and that assumes that there is indeed something that you can compare it with. We call it a gold standard or a ground truth. And obviously, if there are issues with your ground truth, then there will also be issues with the way you compare your predictions with it. There are different ways to score them. We'll go over a couple of measures and a couple of different plots that you can use to evaluate how well you predict your gold standard. And the case that we'll examine to go through this is the Reed paper that most of you should have read for today about remote homolog detection. So today's going to be structured roughly like this. We're going to talk 30 minutes about benchmarking, then we're going to split the entire group into smaller groups where you will answer one question each. And we're going to reshuffle those groups so that you can explain the answers to the questions to each other. And then finally we address those colloquially again. And in the end we will have a slightly more in-depth discussion of the tail end of the paper. So, our needle in a haystack. Specifically for your project, what we want to know is how good are these blast hits that you found. So if you find a protein mapped to another protein with a very low E-value, is this actually a homolog or not? So this obviously depends on how similar the sequences are, and for really close homologs, it's really unlikely that such an E-value would happen by chance. For more remote homologs, however, you would expect a far higher E-value because the sequences diverged a longer time ago, and there are many, many more chances or ways to get such a high E-value, so it's more difficult to assess this reliably. Just for the sake of definitions, right? Who knows what exactly is a homolog?
Genes derived from a common ancestor.
Exactly. Is this only for genes?
No.
Alright, so the answer is, of course, that a homolog is something that is derived from common evolutionary ancestry. Very good. Right, and obviously in your benchmark you need to balance your low and your high E values if you want to capture all of the homologs. Who here has seen a table like this before? Alright, who has not seen a table like this before? Come in.
It's closed.
Don't come in. It's not locked on. Right, confusion table. So on the where is it? There. On the y-axis in this table is what you have predicted. So if you find a low E-value in your blast hit, then your conclusion from that might be that this is a putative homolog. If you find a high E-value in your blast hit, then you probably would predict this not to be a homolog. Benchmarking now, because it's a binary classification, comes from comparing this with some truth. So in reality, if something is indeed a homolog, then this would be a correct prediction, or a true positive. And predicting it not to be a homolog would be a false prediction, or a false negative. So your prediction is negative, but it's not true, so it's false. If reality tells you that it is not a homolog, then if you had predicted it to be one, your prediction is positive, but you're wrong, so it's a false positive. If you had predicted it not to be a homolog and it is indeed not one, then you have a true negative. Right? I'm going to put this on the board because we're going to refer back to it a whole bunch of times later on. So you have here your prediction, and you have here your reality. So if this is hit, and this is no hit, whereas this is true, no, not true, this is homolog versus not homolog. And here we have our true positives, here we have our true negatives. And again, this is a positive prediction, but you're wrong, so this is a false positive. And this is a negative prediction, still wrong, false, negative. For those of you who followed statistics courses during your master, you might also recognize this as a type 1 error versus a type 2 error. We don't always consider these to be equally important. Can someone think of an example where we, as a society, consider false negatives to be less terrible than false positives? Any takers? Yes?
Well, in the case of medical diagnosis, if you diagnose someone with cancer and needs treatment, then you have a wrong prediction.
True. So if you treat someone for a disease that they don't actually have, that would be terrible. However, in diagnostics, it's actually quite common to optimize for the other one. Anyone know why?
Rather treat just in case.
It's not necessarily about treatment, it's about detection. So if you take, for example, a doping test, and you get a positive result even though you didn't actually do doping, it's much easier to simply run the test again and again until you're confident that it's really true, than it is to let a cyclist, get an unfair advantage in his race. Now, you can debate about whether or not this is good, but we have as a society decided that in the legal system, for example, it's much worse to have false positives than it is false negatives. In this case, that would mean convicting someone for a crime they didn't commit versus letting someone go because you're not really sure if they did it. In bioinformatics, we're not going to think about this too much. We'll get back to this at the end of the lecture, perhaps. But for the rest of this lecture, we'll consider false negatives and false positives to be equally bad, because this is how most of the metrics work. Yes?
The categories in which hits occur, so it's hit in the same category. Would the category be a superfamily or is it in the main family?
Okay, so the question is about scope, if I'm not mistaken.
What?
Scope? The structural classification? Yes?
Yes. For example.
So, a hit in the same category as your query, what level of scope would you consider to be a category? Is that the question?
Exactly, yeah.
Right. I'm not going to answer that, because this is something that you have to consider for your project. And there is right and wrong answers here, but even in the documentation of scope, you will find that they say that certain levels of classification are more directly related to whether or not proteins share evolutionary ancestry. So I'll let you find the answer to that on your own after class. Any other questions? Moving on then. Alright, so we've been over this. A true positive is a correct prediction, false positive is a wrongly positive prediction, true negative is that you correctly predicted it not, and false negative is a reality true that you missed to predict. Okay. Again, not sure why the slide is duplicated. Right. This is more things that we're going to do on the board. So these are a couple of metrics that you can use. No, we're not going into metrics yet. We're going to go through a simple example. Now, in the interest of time, because there's a lot more students than we were used to from last year, we're only going to do this with the front 3 rows. We're going to try and predict someone's gender from the length of their hair. And I know it's 2018, so binary gender classification is really not done anymore, but for the sake of exercise, we're going to assume that this works, right? I'm going to make a little table here, and then we're going to score from the front line everyone's gender and hair length. So we have female, we have male, and then we have short and long. The underlying model, again, being that women have long hair, men have short hair. So we're just going to count the front rows. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 women. How many of those have long hair by their own count? 1, 2, 3, 4, 5, 6. So we have 6 long hairs, 4 short hairs. Is that correct? Good. 4 versus 6. Not off to a good start. Males now. Short hair. 1, 2, 3, 4, 5, 6, 7. 7 males with short hair. How many have long hair? 1, 2, 3, 4, 4. Excellent. All right, now we're going to try some of these metrics that we've been talking about. Right, so going through these one by one, we'll take our time. I'm sure you've seen a lot of these terms before, but because we're going to use them now, we're going to write them on the board as well. Sensitivity, also known as coverage, recall, true positive rate, is the amount of true positives divided by the total amount of positives. So TP divided by, moving over here, sensitivity is true positives divided by true positives over false negatives. Specificity is related to it, but it's on the other axis. So it's for all the negatives. It's your true negatives divided by the true negatives plus false positives. Right? So if you look up in your confusion table again, it is this column, and it's specifically the weight of this cell in that column. So specificity equals true negatives divided by false positives plus true negatives. The error is the complement of specificity, so it's 1 minus that thing, or it's false positives divided by these two. Back. All right. Precision, or positive predictive value, is now about this row instead of columns. There's your true positives divided by the true positives plus false positives. So of all your positive predictions, how many of those were right? Precision equals true positives over true positives plus false positives. And then finally your error per query, which is a term that you will have found a lot in the graphs in the paper as well, is the amount of false positives divided by all the positive predictions. So again, it's the complement of precision. It is this one divided by the sum of these two. Yes? So your EPQ equals false positives divided by true positives plus false positives. Now the reason I wrote this all on the board is that I'm going to move away from this line, and now we're going to calculate it ourselves. So I would like to know, for our little test data set, what is our sensitivity, specificity, error, precision, and error per query? So please take a moment to calculate these on your own, and we'll go through the answers in a minute. All right, first one, sensitivity. Who dares? Simple arithmetic. One of you has to know this.
I think it's well, if you go by male, take a male with short hairs is true positives, and female with long hairs is true negatives, just for the sake of it.
Right.
You can do it the other way around. So then the sensitivity would be 7 divided by 11.
Yes.
And the specificity would be 6 divided by 10.
All right, so we have our true positives, which you think is males with short hair,
Yeah.
divided by that column, which is indeed 11. And then we have our specificity, which is true negatives, in this case, females with long hair, which is 6 divided by 10. Everyone agrees? Good, we're writing this down. I can't do 7 divided by 11 off the top of my head. Someone have a calculator for the fraction. No? We'll do it exactly then. So, 7 divided by 11, and 6 divided by 10. Alright, now we know that the error is the inverse of one of these things. Specifically, it is 1 minus 6 over 10 or 4 over 10. Now the precision. Of all the people that we have predicted to be male, how many of them actually were? Very straightforward, no? So it's a bit unfortunate that we have 4 on both the diagonals, but this makes it really easy to fill out. So again, we have 7 over 11 here, and now we have 4 over 11 for the error required. For the sake of argument, right, what would have happened to these scores if we had inverted what we consider to be a positive? So if we had considered long-haired females to be true positives and short-haired males to be true negatives.
The PR in the slide is for PPV.
Yes, so I'll actually go back to that slide real quick. All of these metrics, where's my pointer? There. All of these metrics have very many different names, because statistics confuse people, and confused people come up with new terms for things they already knew. If you look up on Wikipedia, there is actually this huge table of all the statistics you can derive from a simple confusion table like this one. And each of these metrics goes by at least 3 different names. We'll use these ones for the rest of this lecture, but you will likely encounter different ones spread out through the literature as well. Coverage, for example, we will also use here. Right here. Coverage is, sensitivity is. Right, but the PPV is the same as prediction. It's the complement of error per query, which is also the negative predictive value. Okay, so we've calculated all these things. Now, some questions. What could we have done different to make sure that we get all the positive predictions right?
Sorry, but the error is 1 minus the specificity,
Yes.
and the specificity is left. Okay.
Did it fall into place? Okay, so specificity, right? True negatives divided by the actual negatives in the data. So it's this cell divided by this column. The complement of that, the error, is this cell divided by this column. Now you know the column only has 2 entries, so if you sum them up and let that equal 1, then 1 must be the other divided by. No?
Yeah, so
Right.
I see now I changed the specificity and sensitivity.
Yes. So because all these things have so many different names, and because they all look so much like one another, we wrote them down here. Because we will be referring to these all, and I was getting confused as well. Now, where were we? Right, predicting all known cases, sticking to the interpretation that a positive prediction equals male. What could we have done different to make sure that we get all the males predicted?
Find the boundaries of the measurement short or long.
Exactly. So if you change the length at which you consider hair to be long versus short, for instance, if we only count hair longer than 2 meters to be long, and everything less than that to be short, then what would happen is that you predict everyone to be male. Right? In that case, you're absolutely guaranteed that you get all the males right. However, on the flip side, what happens?
All females wrong.
Exactly. So if you predict everyone to be a male, then obviously you get the males right, but you also get all the females wrong. Bad day to be a woman. Which of these metrics best covers now the fact that we got all the males right? These metrics are scored between 0 and 1. Which of them becomes 1 if we predict everyone to be male? Exactly. So the inverse, obviously, how do we prevent making any mistakes? In this case, how do we make sure that our false positives equal 0? Predict everyone to be a female. Again, how do we do this with this data set? So we're playing with the hair length cutoff, right? There's no one that is completely bald in the front row, close call, but there are no hair lengths of 0. So if we set the threshold for long hair at 0 millimeters, then everyone has long hair, ergo we predict everyone to be female, so we make no false positive predictions about there being a long-haired man. But again, we get all the males wrong now. So this is the trade-off that your benchmark has to deal with. It is finding this threshold such that you have a high sensitivity and a low error. Now, I won't spend too much time on this, but this is important to have seen at least once in your life. The accuracy for a benchmark prediction you can express as the sum of total positives, true positives, true negatives, versus the complete sum of observations. You can also balance this accuracy by taking your sensitivity and your specificity and taking their average. Difference being that one is less sensitive to class imbalance. And then finally, there's a really complicated equation here at the bottom. It's really not that bad, but this is useful if you're doing bioinformatics, because it's less susceptible to class imbalances than, for example, the accuracy score or a very popular method, the F1 score. I think we've already gone through this now. Right, so how could we optimize accuracy and sensitivity for these predictions? If we want to best be able to reproduce what is indeed a female and a male, we've already discussed that we have to play with what we consider short and long hair, right? So how would we go about this? Trying to find the best hair length to reconstruct these predictions.
Change the hair length until you get optimal accuracy.
Exactly. So there is a standardized way of plotting this. I'll come back to this slide in a second, but I want to show you that slide first. So this is a receiver-operated characteristic plot. Now, you all have to make these for your projects, and they have to be part of your draft reports. So it's important that you understand what happens here. Starting from the example we just had, right? Suppose that we predict everything to be negative, then your true positive rate and your false positive rate, or your sensitivity and your error, both equal 0. Now, if you predict everything to be positive, then you end up in this corner. So your true positive rate equals 1, but you also got everything wrong that you could have gotten wrong, so your false positive rate is also 1. Looking at the table, what we're effectively doing, right, is we're shifting everything from this row to this row. So you start out with 0 values here because you predict everything negative, and you end up with 0 values here because you predict everything positive. In between those two extremes, you gradually slide your hair length cutoff from 0 millimeters to 2 meters, and in doing so, you move values from the male to the female. From the male to the female row, one by one, based on whose hair next crosses the threshold. You'll do the same in your projects, where you increase the E-value threshold at which you consider a protein to be a homolog, from absolute 0 to ridiculous infinite. And in doing so, you consider everything to be not a homolog, to become a homolog in order of their E-values. What this plot shows you then is the best possible performance that your method can achieve. So for a perfect prediction, the ROC plot will go from 0 to the top left corner, in which case you get everything right. And then from that point on, you start making more false positives until you have predicted everything to be a positive incorrectly. So at this point, your true positives are perfect, so your sensitivity equals 1. You have no false positives and no false negatives. Your true negatives are also perfect, so everything that is a positive you predict correctly, everything that is a negative you predict correctly. Compare that to the performance of a random method. So if you just, by random, declare this is a positive, this is a negative, what would your AUC or your ROC plot look like here?
Like the black line.
Exactly. So this line here represents the performance of a random method. It has an area under the curve of 0.5. And basically it's, well, like we defined, completely random, whether you get something right or wrong. In the rare case that your area under this curve is less than 0.5, what could you do to immediately improve all your predictions?
Inverse it.
Yes. So if it should ever happen that your method scores worse than random, then you're better off inverting your predictions. This should never happen, but you see some pretty crazy things in data science. Right, so that's what a rock plot looks like. These are all common ways of visually evaluating your benchmark. So a rock plot will plot coverage or true positive rate against error, or 1 minus your specificity. This is why we wrote things down. In the paper, you've also seen coverage versus error per query plots. And we will ask later why this makes sense to investigate. And the plot that I'm going to show you next is a precision recall plot, which looks a little like this. So again, question.
Are you also allowed to give your matrix some costs?
Sorry, can you repeat the question? I didn't hear it.
Is it also possible to give you your matrix some costs so you can optimize it?
Some cost?
Yeah, like you want to not have a true negative, so you give it a lot of cost, like 10 euros each, and the other ones you can make cheaper.
Like weight?
Yeah, like weight.
Right. I'm not sure if I completely understood the question, but I think this is about weighting your type 1 versus type 2 errors.
Yeah.
Right? Yes, this is possible. No, we're not discussing that today, because it's actually rather complicated.
So you're not allowed to do it in the project.
I would recommend against it,
Okay.
because it makes it much harder to compare your results against those of other groups. If you can make a good case for why you should, because you have seen in literature that this drastically improves the performance of given methods, then by all means. But there's a lot of extra work for yourself in the group, so only do that if you have that time to spare. Right, precision recall plots. This is effectively constructed in the exact same way as the rock plot. So you shift all your predictions from negative to positive, gradually crossing 1 point per threshold. The difference here is what's on the axes. Now instead of sensitivity, we have precision on the y-axis. Just to remind you guys, this is the true positives divided by all positives. So it's this cell divided by this row, and relates only to your predictions. It's not immediately grounded to whether something actually is a hit. A recall on the x-axis. I did not write down what recall is, did I? All right. It is the true positives divided by the sum of true positives and false negatives. So it is actually the same as sensitivity off the top of my head. I'm just going to go back in the slides to make sure that I'm not misleading you here. True positives divided by this column. Right, so it says recall on the x-axis here, but it is also the same as sensitivity or coverage. If you change your predictions from everything negative to everything positive, what point will you end in? So when you predict everything to be positive, what is your precision? If you predict everything to be positive, we look here at prediction, precision, right? Then your true positives divided by the true positives plus false positives will account for everything except your false negatives. Agreed? I see a lot of blank stares. I'll try that again, because it's really difficult to phrase this precisely. You see here on the right end of the axis that a precision of about 0.2 is reached by these three methods, which we won't discuss. That means that in the data set, if you predict everything to be positive, your precision, the true positives divided by true positives plus false positives, equals 0.2.
It's the amount of true positive divided by everything.
Yes. So this tells you something about the amount of actual positives in your data set. This in turn means that the random performance, or the performance of a random model in a precision recall plot, will be this horizontal line. It also means that everywhere you are higher than that line, your method performs better than random. Does everyone get that? Well, we'll play some more with this during the questions that you need to answer, which is not about a precision recall plot, but about the coverage error per query plots in the paper. So, how do the axes relate between a ROC and PR plot? We've been over this, but they inherently ask different questions. There's someone there that has a guess what question your ROC plot answers best versus what question your precision recall plot tries to answer. Yes.
And first, whether your test focuses on reducing type 1 and type 2 errors. It shows what you find more important. If you find specificity higher or selectivity.
Okay.
Positive and false positive. I would say second, how well the test performs depending on the true ratio of hits and misses.
That's close.
So
I'm trying to rephrase that slightly.
Yeah.
So we discussed, right, that a perfect method will go through the top left corner. So what your ROC plot shows you is, given this method of prediction or benchmarking, how close it was possible for you to get to perfect score. Right? Because for every possible value of a threshold, the closer you get to this top left corner, the better your method's accuracy. The precision recall plot shows more about the distribution of your data. Of course, again, in relation to your predictions. But if you have a lot of positives in your data set, then this random predictor line, which isn't drawn, but you can imagine it, would be higher or lower. Whereas the way in which you approach that line says something about how well your method approaches predicting things. Really difficult to phrase this in a way that comes across well. So we will discuss this more later on. Speaking of, I'm going to split you up into groups now. Yes?
I have one more question about the asterisks, like the standard threshold.
Sorry, one more time.
So,
The asterisks,
yeah.
the standard thresholds. Oh, excellent. Move it forward again. Right. So, what I wasn't going to discuss originally is what these three methods are. They are actually work from Anton and a former colleague of mine about predicting protein-protein interactions. So these are three different methods used to predict whether or not two proteins interact. The curves, as we've discussed, are constructed by changing your threshold from predicting everything negative to everything positive. And then at the point of these asterisks is where the default threshold for these methods is set by the people that published it. Does that answer your question? Good. Now then, I'm going to split you all into groups, and I'm going to assign you one question per group, about the paper that you have read for today?
How big should the group be?
Good question. Given the number of people in this group, I'm going to say that we will aim for 8 people per group. Or maybe I'll just do it by rows. Yes, most rows seem to have enough people to make a group out of, so we're going to do that. All right. I'm going to put the question on the board. Just a moment, everyone. First row, question 1. Second row, question 2. Third row, question 3. Fourth row, question 4. Fifth row, question 1 again. Please count the rows and figure out what question is yours. All right. Now, just a second more. Before everyone breaks into debate, I think this is a good point to have a little break for everyone to go grab some coffee, stretch some legs. Stay with the people in your row. Please return to the same rows when you're done. And then go discuss these questions open hall. I'll see you all back here at, say, 10. Actually, got
most interesting or most useful method.
That's your mama.
Ja, dat zijn ze. Ja, oké. Dan niet zo doen dat een ijsje nu wel mee. Ja,
Fine. Yeah, I'll read that. Yeah, okay, I'll come with you.
Wait, what's your question?
Oh, yeah, we all have the same question, of course.
No, it's the same.
Yeah, we have the same one. So what do you think? Do you think anything about questions from beginners and answers?
Actually, but I have to remember all the different references. Yes? Yeah? Well, if you have a computer science background, then you shouldn't count the problems.